Hello and welcome to this online lecture. This is Dr. Maharaj, your first lecturer for Separation Processes 2. In this online lecture, we will be looking at preliminary considerations in column design. So the first consideration would be that of the key components. And these are the components between which the separation would be determined. The distribution of the components other than the key components cannot be specified, but will be determined during the calculations. The separation between the key components can be specified by mole fractions of the light key component in the bottoms and the mole fraction of the heavy key component in the tops product. It could also be specified in terms of flows. For example, the percentage recovery of key components in the feed, say 95% of flow of light key component in the feed will go off in the tops, and 95% of the flow of the heavy key component in the feed will go into the bottoms. Or the separation between the key components may be specified by an appropriate combination of the first two considerations that were listed in A and B. In the specification of multi-component separations, it is necessary to select the two key components and specify their distribution between the distillate and the bottom product streams. The distribution of the other components cannot be specified, but rather they would be determined by the design conditions that were selected to accomplish the specified separation of the key components. The second consideration in column design would be the feed conditions to calculate the L and V values in the column. For example, if the feed is at bubble point, or in other words, if it is a saturated liquid, the feed could also be a saturated vapor, or it may be a mixture of liquid and vapor. In other words, a thermal condition between the bubble point and the dew point. A flash calculation would determine the amount of vapor and liquid, and flash calculations were done in section 3.4 in the previous lecture, which you can review. The third consideration would be that of the column pressure. The column must operate over a practical range of temperatures, and it is therefore necessary to operate at such a pressure that the liquid mixture can be boiled over a practical and economical range of temperatures. We would use cooling water temperature as a guide, say at a range of 30 to 35 degrees Celsius, and the condensing temperature at around 45 degrees Celsius. And we need to determine a pressure that allows the top product, that allows the tops product to boil at 45 degrees Celsius. We can also assume that steam needs to be 150 to 200 degrees Celsius for a reboiler. We assume that the bubble point pressure is 25 bar and a dew point pressure would be about 20 bar. For a partial condenser, you operate between 20 to 25 bar, and a dew point pressure of vapor leaving the top of the column at about 45 degrees Celsius is 20 bar. If there's a cold liquid reflux, the operating pressure will be greater than 25 bar. So I'll say that again. To determine the pressure that allows the top product to boil at 45 degrees Celsius, and we're assuming our bubble point pressure is about 25 bar and the dew point pressure is 20, for say a partial condenser, where we're operating between 20 and 25 bar, the dew point pressure of the vapor leaving the top of the column at 45 degrees Celsius would be about 20 bar. If there's a cold liquid reflux, the operating pressure will be greater than 25 bar. Some other factors in the choice of pressure: as the pressure decreases, the vapor volume would increase. So as the pressure decreases, the vapor volume increases, and for a given vapor flow rate, we would need more column diameter. However, if we increase the pressure, we effectively reduce values of the equilibrium constant. So increasing the pressure reduces the K values, and that implies that we would need more stages for a given separation. We can now go further into multi-component distillation column design. The basic function of a column design is to determine the number of theoretical stages required to achieve that would be required to effect a specified separation of the key components. We would need to consider our feed composition, flow rate, and thermal condition, as well as the column's operating pressure and the required separation of our key components. We also need to consider the thermodynamic properties of all of the components, so equilibria and possibly enthalpy data. We would need to know our operating reflux ratio. So the design methods for multi-component distillation are based on tray-to-tray calculations. We calculate the effluent phase concentrations at each stage. The tray temperature may also be calculated if the boiling point method is used for equilibria rather than the relative volatility method. Three types of relationships that are used in the calculations are equilibria, material and component balances, and enthalpy balances. As we would do in the case of binary systems, if a condition of constant molar overflow may be assumed, then the enthalpy balance relationships don't have to be used, and the calculations would be considerably simplified. Let us now take a look at the inside sketch of a distillation column in which the stage numbers are I in the rectifying section, that is the stage above the feed, and the stage numbers are K in the sections below the feed. Our component number will be assigned an arbitrary say letter like say J, and I would invite you all to pause this video at this point and carefully review the figure. You may even practice drawing the setup to develop the relationships that we will see. So if we look at the diagram, we see that we have a vapor flow rate in the rectifying section that we will call VR. There is some condenser here that will condense our TOPS product, QC being the heat removed at the condenser. We take off our distillate D, having a composition XD for a particular component J, and which also carries some enthalpy HD. What is refluxed back into the column is denoted by our flow rate here, LR, the flow of liquid, our liquid flow rate in the rectifying section. Here we have our feed into the column with its composition. Coming in to any tray I in the rectifying section, we have our vapor flow rate, and since it's coming into stage I and the top tray is numbered 1, we say then that the vapor is coming from a stage below I, which is say I plus 1, with a composition Y, I plus 1, and a given enthalpy. Leaving stage I would be some liquid flow rate Li, having its own composition and enthalpy. Below the feed stage, we see that as we go down, we would have some arbitrary stage called K, and the final number of stages in the column is denoted by N. So the stage that would be above K would be called the stage K minus 1. Leaving stage K, we have a vapor flow rate Vk with its own composition and enthalpy, and entering that stage would be Lk minus 1, that's the liquid flow rate with its composition and enthalpy. The vapor flow rate in the stripping section would be Vs, and the liquid flow rate Ls. This here is our reboiler with its associated heat that is added to recycle some vapor back into the column. Coming out of the bottom of the column would be our bottoms product stream W, having its own composition and enthalpy. Let us now take a look at our equilibrium relationships. So for a component Yij, it is given by Kij, Xij, and the summation of all of our vapor compositions would be equal to 1. Similarly, summation of all of our liquid compositions would be equal to 1. These were some of the relationships that we derived in the last lecture in terms of relative volatility. So we can use our equilibrium relationships in terms of the equilibrium constants, or K, which would be our boiling point method of determination, or we can get our compositions using the concept of relative volatilities. These equations being derived Yij is equal to alpha ij xij over the summation of the product of alpha ij xij, j going from 1 to n, or similarly xij being given in terms of relative volatility as the ratio of Yij over alpha ij to the summation of all of the ratios of Yij to alpha ij, where j goes from 1 to n. Pause this video at this point and, using the diagram, develop the material balances in the rectifying section and the stripping section. Use the red envelope that is drawn around each section as your guide into the flows into and out of that defined boundary in both the rectifying and stripping sections. This should help you develop your equations. If you had gone through that exercise, you should have seen that the material balance in the rectifying section would have given you Vi plus 1 Yi plus 1 J is equal to Li Xi J plus Dx Dj, and for the stripping section, Lk minus 1 Xk minus 1 J is equal to Vk Ykj plus Wxwj. Pause the video again and do an enthalpy balance across the rectifying and stripping section. The enthalpy balances being developed would be total enthalpy balances. And you would see then that for the rectifying section we have Vi plus 1 Hi is equal to Li Hi plus Dxd plus Qi for the condenser. And in the stripping section it would be Lk minus 1 Hk minus 1 is equal to Vk Hk plus Whw minus Qb. the enthalpies in these equations are total enthalpies. In other words, they are enthalpies quoted for gas and liquid mixtures. The enthalpy per mole of vapor, Hi plus 1, capital Hi plus 1, and the enthalpy per mole of liquid, common Hi, may be given by, say, these relationships here. The summation of the product of the enthalpy per mole of vapor by the mole fraction, and for the liquid, it would be the enthalpy per mole of liquid multiplied by the mole fraction, and we find the sum of those products. Now, if we assume constant molar overflow, the values of L and V in the rectifying and stripping section may be assumed to be constant, and the material balance equations would reduce to these two here. In the rectifying section, we would have VR yi plus 1j is equal to LR xij plus d xdj. And in the stripping section, we have LS xk minus 1j is equal to Vs ykj plus w xwj. The method of applying the given relationships that we developed would be by tray-to-tray calculations or the Lewis-Mattison method. We will take a look at that in our next lecture. Thank you. If you have any questions, please let me know in the online forum.